Chapter 11, Multinomial Logistic Regression. In this chapter, we will discuss an approach of estimating the class probabilities for a multi-category response, and we use these probabilities to classify new cases into one of several outcome groups. Assume that we have G possible outcomes, 1 through G, with multinomial probabilities, where the probability of Y equals K equals the probability of K, where K is from 1 through G. Therefore, the P of 1 equals the probability of Y equals 1, which is 1 over 1 plus the summation of H equals 2 to G of the exponent of alpha sub H plus X beta sub H. And the P of K is the probability of Y equals K, which is equal to the exponent of alpha sub H plus X beta sub H over 1 plus the summation of H equals 2 to G of exponent alpha sub H plus X beta sub H, for K equals 2 through G. The probabilities sum to 1. The log odds interpretation of the logistic regression model is log PK over P1, which is equal to alpha sub H plus X beta sub H for K equals 2 through G. However, there are several drawbacks to these models. First, the models involve many parameters which make their interpretation tedious. Fortunately, the main interest in data mining is not so much the interpretation of the parameter estimation, but the estimation of the class probabilities and the classification of a new case with given covariate feature vector X. The second is maximum likelihood estimation, or the MLE, of logistic and multinomial logistic models encounters numerical problems if the data is separable and if the predicted probabilities are close to either 0 or 1. The computer softwares are, several choices are available to estimate multinomial logistic regression models in R. One can use the command mlogic, the command vglm, the mnlm function. These packages differ somewhat with respect to the data input, the model parameterization they adopt, and the estimation approach they use. The first example is forensic glass. This dataset contains 214 cases, 6 categories, and 9 predictors. This data set contains those categories, so we need to install the packages first. We need to install VGAM, which estimates multinomial logistic regression, text.R to standardize the features, and MASS, which is the library of example datasets. And we use the dataset FGL, which loads the data into R. Now standardization, using the normalize function in the library text.R. In this scenario, we have to change the normalize function to scale. And then we get the standard deviation, which to convince yourself that features are standardized. And we get the summary. Each coefficient vector contains 3 elements, as there are 3 covariates in the model. The model contains 20 parameters, which are estimated on 214 cases. So we have to predict the new summary and obtain the log odds relative to last group. The predict command returns for each case I with features xi, the fitted logits alpha sub k hat plus xi beta sub k hat. For each of the 214 cases, we obtain 5 logits, where k equals 1 through 5 as there are 6 groups, with the last group being used as the standard. And we rounded the fitted, and we get the probabilities. The predicted probabilities for the first couple of cases, together with the actual classification, are shown. Now we bind them together and we round it, and we can get the box plots of the estimated probabilities against the true group. So we plot the probabilities of group memberships against group. For each group, we construct a box plot of its estimated probabilities using the estimated probabilities of those shards that were known to come from that group. A good model should give us large probabilities in each of the 6 groups. The results show that we are doing poorly in identifying vehicle and table glass, but much better in identifying head glass. Most probabilities for WinF, WinNF, and table glass are in the 40 to 60% range. Next, we evaluate the performance of the multinomial logistic model in terms of its out-of-sample prediction. We select a training set of 194 cases at random, estimate the model on these 194 cases, and use the model to predict the probabilities of group membership for the 20 cases that have been withheld from the estimation. So we do the second program, where we have the estimation on all 194 shards, and we predict the 20 new cases, performance in predicting a single set of 20 new cases. We have to load the same libraries back in, scale it again, and then we do the new prediction. So we can calculate the probabilities from the predicted logits. Now, the proportion of incorrect classifications, here 5 of 20 or 25%, depends on the selected test data set. In order to obtain more stable estimates, we replicate the analysis for 100 randomly selected test data sets, and we do the third program by loading the same libraries back in, scaling, and now we do the out-of-sample prediction. And we get the proportion of correct classification with the new box plot. Before we get to the second example, we're just going to do the appendix, which is a specification of the simple triplet matrix. A simple triplet matrix is a very efficient representation of a large but sparse matrix. Consider an n by m matrix of counts, where n represents the number of cases and m is the number of categories. Each row has a 1 for the observations category and zeros elsewhere. We have to download the library SLAM, which helps do the simple triplet matrices. Here's a 6x2 triplet matrix. Now we can do the same thing. And we can get a 6x6 simple triplet matrix. And lastly, we could just test it out for a 16x6 simple triplet matrix. Next, we can get to the second example, which is the forensic glass revisited. So the second example is the forensic glass revisited. Until now, the analysis considered only 3 features. Next, we consider the full dataset with all 6 classes and 214 cases. So the first program is the cross-validation to determine the penalty in MNLM. We download everything back and we do the normalize function. Because the MNLM function does not work with my version of R, we will use the textbook to look at our output. We get the proportion of the correct classifications using the Laplace scale penalty, which should look like this. The next program is the detailed MNLM output for the penalty equals 1. The annotated output of the analysis with the Laplace prior lambda equals 1. So we load the data back in and we do everything again. And when we can observe that quite a few of the estimated coefficients are 0 and many of the variables are not entering the logit equations. This command calculates the fitted count expectations, the as.matrix of the fitted glass LM. Then we can plot it. After plotting, here we plot the probabilities of group membership against group. The results show that we are still doing poorly in identifying vehicle glass, but somewhat better in identifying head glass. The results are only a modest improvement over those of the model with just NA, MG, and AL. Fitting the multinomial logistic regression model with penalty lambda equals 1 to the 194 shards that have been randomly selected from the 214 shards, predicting the probabilities and classifying the remaining 20 items, and repeating the out-of-sample prediction classification 100 times leads to 65% correct classification. This is not much of an improvement over the results of the multinomial logistic model with just 3 covariates, which was 60%. Next, we're going to do the third program where we estimate on all 194 shards and predict 20 new cases with the multinomial logistic regression with linear logits. After getting the next box plot, we enlarge our model by including all interaction effects. This new model includes 1 intercept, 9 linear coefficients, and 36 cross products, for a total of 46 terms, and 230 coefficients as there are 6 possible outcomes. Lastly, we will run the fourth program, the estimation on all 194 shards and predicting 20 new cases, multinomial logistic regression with linear and cross products. So we do the x of 1 by 3 to see the contents, and we remove 1 from the intercept. We get the dimension, which x has 45 columns. And then we shall get the new box plot, which in this case we cannot because it does not work with this version of R. That is all.